All right, in this last part of lecture 22, we're going to talk about what's the difference between a polar molecule and a nonpolar molecule. Now, those terms probably sound a little familiar from what we were just talking about, right? But in the previous part, we were talking about a bond. So they are related, but they're not exactly the same thing. So let's kind of quickly review what do I mean by a polar and a nonpolar bond. Well, the way you tell if you have a polar bond or a nonpolar bond, right? You look up your electronegativities. And depending on how far apart they are, if those electronegativities and the atoms that are bonded to each other, their electronegativities are 0 to zero point 0.4, that's a nonpolar bond. If the difference electronegativities is zero point 0.5 to 2, that's a polar bond. And if the difference electronegativities is more than 2, that's an ionic bond. So the way we tell whether a bond between two atoms is polar or not is we look up the electronegativities and basically subtract them. Now, it turns out a related thing is that an entire molecule can be polar or nonpolar. So let's talk about what that means. And it is related, but it's not exactly the same thing. All right. So molecules can be polar or nonpolar overall. Now, what does it mean to be polar? Polar molecules contain charged areas. We'll say contain charged areas. Nonpolar molecules will say do not contain charged areas. And I have to say, this is one of these topics where like we kind of notice the effect of things being polar or nonpolar all the time in our life. It really, for example, has to do with, you'll notice when things mix or don't mix, that really has to do with polarity. So for example, you might go into your refrigerator tonight and you might grab a bottle of like salad dressing, like Italian salad dressing, and you might notice there's two layers, right? There's an oil layer on top and then like a vinegar or we could say water layer underneath. Now, why does that happen? Why is it that oil and water don't mix? Why do they make layers? Well, it turns out it has to do with this topic. It has to do with polarity. If things are opposite, one's polar and one's nonpolar, they're not going to mix. And that's exactly what is going on in oil and water. Oil is a nonpolar substance. Water is a polar substance. So if you are opposites, polar and nonpolar, you do not mix. All right. So there's plenty of things in the world that where two liquids, for example, will mix, and that also has to do with polarity. Like for example, you might go into your refrigerator tonight, and assuming you're 21, you might get out of there like a bottle of beer, like I don't know, Duff beer, like Homer Simpson likes. And in Duff beer, there's two liquids as well. There's alcohol and water. Now, it turns out the reason why they mix, why the alcohol and the water are mixed, there's not two layers, is that alcohol and water are both polar. All right, so when you are the same, if you have the same polarity, both polar, or it would actually work with two nonpolar things, sames, we'll say, will mix. All right, so understanding like or trying to figure out whether something is polar or nonpolar, that's going to help us understand the properties that materials have. It helps us to understand, for example, why things mix and why some things don't mix. It also will help us with some other properties that we're going to get into in a future chapter. All right, so really we need to be able to determine based on like a formula, based on thinking about what atoms are in a molecule, is this molecule going to be polar or nonpolar? So what do you need to be polar? For a molecule to be polar, first off, number one, you must contain polar bonds. So polar molecules contain polar bonds. That might sort of make sense, right? It sounds like they should go together, doesn't it? But it turns out that's not enough to be polar. Polar molecules, not only do they contain polar bonds, they also have to have something else. to become polar overall. And that something else is, well, there's actually two options. And either a lone pair on the metal atom, we could say at least one lone pair, a lone pair on the middle atom, or the other option is, we'll say, different atoms attached to the middle atom. Different atoms attached to the middle atom. Now, there's kind of a fancy word for this. That's called being, these options here are things that are going to make you asymmetrical. Asymmetrical. All right, I won't worry about that too much, that word, but you might see it in your book or whatever. Okay, so we're going to get to examples in a minute, but let me just go over this one more time. So to be polar, you have to have a polar bond. All polar molecules contain polar bonds. But just having polar bonds ain't enough. You also, on top of that, in addition to having polar bonds, you either have to have a lone pair, that would work, polar bonds and a lone pair on the metal atom, that works, or polar bonds and different atoms attached to the middle atom. So one of those two have to also be there. Polar bonds with lone pairs on the metal atom, or polar bonds with different atoms attached to the middle atom. Now, it probably is going to help to see some examples. So let's go over, I'm going to flip over to one more slide, and we're going to go through like all the possible scenarios you could run across. Like there's really only 4 scenarios that could happen. So when we try to think about whether something's going to be polar or not. All right, so let's say we want to determine whether these molecules are polar or nonpolar. All right. So one thing I should tell you, before you want to, if you want to decide whether a molecule is polar or nonpolar overall, you can't do it by just looking at the formula. You really need to take the time and draw out the Lewis structure. So step 1, if we want to know whether something's polar or not, is to make or draw out the Lewis structure. Now, we've already talked about doing Lewis structures. For this lecture, I'm just going to put them up. I'm giving everybody 8 electrons. Hydrogen only needs 2. I'm using the right total and all that. So for example, if we look at our first one, HCN, the Lewis structure, if I follow all the steps, this is what it looks like. All right. Now, after you have the Lewis structure, now you're going to start looking for those requirements. You need to find, if we want to see if this fellow's polar, you need to find at least one polar bond. And you need to find a lone pair on the metal atom. Or different atoms attached to the metal atom. All right. Now, let's start off with our first example here. So how am I going to know if we have polar bonds? I'm going to subtract the electronegativities, right? So I'm going to look them up. All right, so hydrogen, I don't know if I'll circle them because they're over here, right? Hydrogen's 2.1. I'm getting them off the table. Carbon is 2.5. Nitrogen is, what does it say over there? 3. All right, so we're going to look at each bond separately. We're going to look at this bond between carbon and hydrogen. And if I subtract those electronegativities, I get a difference of 0.4. So I'm looking at the carbon-hydrogen bond first. When I subtract electronegativities, the difference is 0.4. That is a nonpolar bond. You have to have a difference of 1/2. All right. So we're going to do the other bond as well. Let's do the carbon-nitrogen bond. Now, I know it's a triple bond. That doesn't make any difference. So we just subtract 3 minus 2.5. Now there, the difference is 0.5. 0.5 or more, you're a polar bond. All right, so we have found polar bonds. We found at least one polar bond. We found it. It's the carbon-nitrogen bond. All right. Now, that's not where we stop. If I want to know whether this molecule is polar overall, I'm going to look at the middle atom, that's my carbon, and I'm going to go, oh, are there any lone pairs on there? And on carbon, no, there's no lone pairs. And then the other way you could be polar, if there's no lone pairs, you might have different atoms attached to the middle atom. We do have that actually. Attached to the carbon, one atom is a hydrogen, one atom is a nitrogen. That's what I mean by different atoms. So we found a polar bond, and we found different atoms attached on the middle atom. I don't really have a lot of room to say that, so I'm just going to say different atoms, but I mean attached to the middle atom. So that means this molecule is polar overall. It's polar overall. All right, we're going to do some more examples. All right, I want to go through all the possible scenarios you're going to see. So let's do another one. Water. This is the Lewis structure for water. Job one, to decide if water is polar or not, you got to look up the electronegativities. You got to see if any of the bonds are polar. I'm just finding them off the chart on the side. I'll just tell them to you to make it a little faster here. So I'm just looking them up. And then once I look them up, I subtract them to see if the bonds are polar or not. So if I want to subtract, let's look at this bond right here. I would subtract 3.5 minus 2.1. That's the carbon-oxygen values, right? That's who's sharing electrons right here. So if I subtract, I get a difference of 1.4. So 1.4, that's what, polar or non-polar? Oh, polar, right? Anything more than a half. Now, I could do the other one. It's going to work out the same way, right? Oxygen, hydrogen again. I subtract 3.5 minus 2.1. I get 1.4 again. So both bonds in this case are polar. When I subtract, I get a difference of more than a half. So we found polar bonds. Yay! So if you find polar bonds, you got to keep looking. If you can find one of these other two things, you're going to be polar overall. Polar bond and, well, wait a minute. Oh, I actually have the first one. A lone pair on the middle atom. I have two sets of lone pairs on the middle atom. This guy and this guy. So I have polar bonds and at least one lone pair on the middle atom. Oh, that's going to make them polar overall. Polar bonds and a lone pair. Again, I mean on the middle atom. Don't have enough room to write it, so just remember that. Polar. All right. Hopefully this is making sense. We're going to go through a few more. All right. Next fella. CH4. Let's draw the Lewis structure. This is methane. I want to decide if methane is polar or not. Draw out the Lewis structure. Now, hunt first for polar bonds. And how do you know? You look up the electronegativities. All right. So we look up the electronegativities. 2.1 for all the hydrogens. This is a little repetitive, but I'm going to do it anyway just to make sure you see it. Carbon is 2.5. All right, so every bond is actually the same thing, isn't it? Every bond is a bond between carbon and hydrogen. And every time, all of them are going to work out the same. If you subtract those electronegativities, oh, I'm going to let you think about this one. If you subtract those electronegativities, carbon-hydrogen bonds, what are they? Polar or non-polar? Oh, I hope you know it is non-polar. So because if you subtract, you only get a difference of 0.4. So they're going to all be non-polar. Every single one of them. They're all identical, really. They're all non-polar. All right. So if you have non-polar bonds, what does that tell me about being polar overall? To be polar, you have to have polar bonds. This thing doesn't even have polar bonds. So I'm not going to waste my time even worrying about the second requirement. I can't even find polar bonds. If you can't find polar bonds, you're going to be non-polar overall. So how should I say that? No polar bonds. All right. To be polar, you have to have polar bonds and more stuff, the lone pair or the different atoms. All right. last scenario. Carbon dioxide, polar or nonpolar? Oh, let's see if we can figure it out. All right, I'm going to do the same thing. Draw the Lewis structure. Look for polar bonds first. How do you do that? You have to know your electronegativities. 2.5 and oxygen is 3.5. At a glance, I don't have these all memorized. All right. So there's two bonds, really. They're both double bonds. That's fine. We're going to look at each one, and actually, they're going to work out the same again because they're really all both bonds between carbon and oxygen. So thinking about either bond, you're going to get the same answer. The carbon-oxygen bond, is this a polar bond or a nonpolar bond? Oh, I'm going to let you think about it again. A bond between carbon and oxygen, polar or nonpolar? Oh, it should be polar. You subtract, you get a difference of 1. 3.5 minus 2.5, that's 1. Anything more than 0.5 is polar. So yeah, oh, wrong color. I don't know, does that matter? It's got a polar bond. All right, so we're going to keep looking. We found a polar bond. The carbon-oxygen bonds are polar. I know that by subtracting. Now, that doesn't mean you're polar overall. We need to find more than just polar bonds. We need to find a lone pair on the middle atom. I'm looking. I don't see a lone pair on the middle atom, carbon. Do you see a lone pair on carbon? I don't see a lone pair on carbon. Nope. Couldn't find that. Or different atoms attached to the middle atom. Different than each other. So like in our first one, a hydrogen and then a nitrogen. The atoms on the sides are not the same. Are there different atoms attached to the middle atom? No. They're both oxygen atoms. So polar bonds, yeah, found polar bonds, but not, no, we'll say no, I should say. No lone pair, no different atoms. What does that mean? Well, this means that it's going to be nonpolar. Oh, I'm running out of room. Nonpolar overall. So because, yeah, we found the first thing, but we couldn't find the other stuff. We couldn't find the lone pair or different atoms. So these are really the 4 possibilities you're going to run across. So these are all the scenarios that exist in the world, okay? So maybe this makes sense, maybe it doesn't. I don't know. We're going to try a little practice and then we'll know for sure, right? So let me put up a couple and I'll kind of get you to help me a little bit on these ones, okay? So let's flip over 2 more examples. Are these things polar or nonpolar? Why do we care? It has to do with the way they're going to behave. We're going to see that in the next chapter. Okay, 2 final examples. Now, I'm going to get you to help me a little bit, but before that, I'm going to help you a little bit. I'm going to draw out the Lewis structures, right? So that's step 1. You got to draw the Lewis structures. You can't just look at the formula. I promise, just looking at the formula, trying to do some shortcut thing ain't going to work. You got to have the Lewis structure. So let me go ahead and write it up here so you guys can all see it out there. And I'm doing it the same way, give everybody 8 and all that. So for our first one, sulfur trioxide, this would be the Lewis structure of it. All right, yep, everybody's got 8 electrons. And then for our next one down there, I'm going to go ahead and do that one too. CH3F. This is what it would look like. I gave everybody the right number of electrons and all that. All right, so the first thing we got to do is we're going to decide if any bonds are polar. And if they are polar, we're going to keep looking for something else to see if the molecule is polar overall. That something else is a lone pair on the middle atom or different atoms attached to the middle atom. So let me help you just a bit more. Let's look up the electronegativities. Sulfur is 2.5. Oxygen is 3.5. They're all the same. I know it's a little repetitive. Really all we have are bonds between oxygen and sulfur. So that bond, look at the electronegativities, polar or nonpolar? Polar. You subtract 3.5 minus 2.5, it's going to be 1. That makes it polar. And again, I could look at any of them. I'll get the same thing. Look at them. They're all 3.5 and 2.5. They're all bonds between oxygen and sulfur. So we found a polar bond. All right. Next question is this thing polar or nonpolar overall? It's nonpolar overall. Now, the reason why it's nonpolar overall is you need to look for either a lone pair on the middle atom. Hey, that's sulfur. I don't see a lone pair on the middle atom. No lone pair. Again, I mean on the middle atom. I don't have room to write it. All right, or you need different atoms. The outer atoms cannot be the same. You need different atoms attached to the middle atom. This time they're all oxygens. So no different atoms. So it's nonpolar overall. All right. Okay, let's do the next one. Same thing. I'm going to look up electronegativities, and first thing we're going to do is look for some polar bonds. 4, 2.5, 2.1, 2.1, 2.1. So this time, just to warn you a little bit before I let you think about it, there's actually two kinds of bonds, right? There are the bonds that are connecting carbon and hydrogen. Those bonds might be polar or not. And then there's the bond that's connecting carbon and fluorine. So you really need to think about carbon-hydrogen and carbon-fluorine. Are either one of those polar bonds? All right, your turn to figure it out. Is there a polar bond in this thing? Yes, there is. If you look at the electronegativities again, the polar bond is the bond between carbon and fluorine. If you subtract there, you get a difference of 1.5. Yep, we have a polar bond. We have at least one polar bond. That means we're going to keep looking. So a polar bond does not make you polar. You have to have more. You have to have either a lone pair on the middle atom or different atoms attached to the middle atom. So think about that. Is this thing going to be polar or nonpolar overall? It should be polar overall. It should be polar overall. Why? Because, yeah, we found a polar bond, the carbon-fluorine one, and we also found, what do you see? There's no lone pair on the carbon, but there are different atoms. Different atoms on the middle atom. So there's hydrogens and fluorine. That's what I mean by different atoms. So that makes it polar overall. All right. With that, I think that's it for this lecture. All right. So if you're struggling in this stuff, it's kind of confusing, well, we'll do some more practice in Zoom, and then we'll, you can always contact me and I'll help you out some more. All right. That's it for lecture 22. I hope you're having a great day. See you soon.